Okay, welcome to section 3 of the electric fields chapter, and what we're going to look at here will make a lot of sense, I think, linking it to gravitational fields. It will help you with the gravitational fields, and we're going to link back to some of the year 12 work as well. So we're going to talk about potential, as in potential energy, but we have a slightly more awkward thing compared to gravity because we have two charges. Not only that, but when we're talking about potential and this idea of being equal at infinity, well, we've got the same thing with electric fields, except you don't have to go to infinity, just like we would be journeying to the moon. If we have a positive and, in this case, a negative charge, we end up with a whole series of ramps and slides effectively within space. So we can talk about the energy gained and lost by these charges. But we have an interesting thing here because all of our definitions are about positive charge. So our definition for electric field strength is the direction exerted by a force on a positive charge. So our electric field strength is away from a positive charge, but it is towards a negative charge. Okay, so that's our basis, which means if we take our positive test charge here, what will happen to that unit charge, 1 coulomb, so just make it easy, 1 coulomb, so that positive test charge, that's going to roll in that direction because it's being exerted on by this positive charge behind it, repelling, or it's going to be attracting. Well, you can think of it as both if you want to make your picture even more complicated. So yeah, repelled away by that positive charge or attracted by the negative charge, our positive test charge will roll down that hill. So we have an analogy just like we do with the gravitational fields. Let's go back a step and look into the chapter first. So within this section, let's move to the section on potential. There we go, section 3. So very similarly to what we had with gravitational fields, we're going to look at potential, the idea of linking it to field strength, and think about the link between them, and think about, more importantly, work done, because it's all about that. So definition for potential at any point, but the any point around a charged object, is we have to think about what that little test charge does happen to it. So we have the idea of potential defined as work done per unit charge, okay, per unit test charge, to move that unit positive test charge from infinity to that point. Okay, so if we work on the idea of electric field, if we go on talking about our forces being 0 out at infinity, just like it was with gravitational fields, that means the potential at infinity is 0 as well. Now we have to do work. If we take our positive test charge, we are going to have that force acting outwards. Okay, so there's our field, and because of that field we have to do the work against that field to get it to there. So for us to get our positive test charge to there, we have to do a certain amount of work. How much work is it? Well, by calculation this was, not by test charging. Okay, so 4 pi epsilon, just like we had before, and similarly to gravitational fields, we've got Q instead of mass over R. Okay, so again, R, not R squared, just like potential for gravitational fields was R with a single mass causing it, so our big test mass, our big mass creating the field there. Only much more sense is to talk about potential in terms of volts in electric fields. Okay, now a little bit extra on here in that If we are talking about a negative test charge, then we get a different effect. If we're talking about the charge being pushed away, repelled, for example, round a circuit, then again, the work is negative because we actually have the work being done by the charge. Okay, so we can start talking about whether we are working against that charge or we are doing the work by that charge. Okay, all our little test charges will move in the direction that the force is exerted. Okay, so the work done is in the direction of the force. Now, just a quick other reminder. We had it easy last year because electric potential is scalar, even though it can be a negative potential. Okay, so again, can it be a negative potential? Only if it's attracting. Okay, so gravity had a negative potential because all masses attract. So that's negative V. Okay, if you are a positive area, then you have positive V. Okay, so unlike gravity where everything was just negative, we can have positive. Which is part of the problem about Franklin originally coming up with his positive and negative charges, getting it the wrong way around. Hence my cartoon on the workbook. So let's move on a little bit and get into kind of perhaps more useful stuff. Now I should say, as I mentioned a second ago, this is all about calculated values, and a lot of it was done by the work and visualization, so we'll have a little look at that in a second. Okay, but what we'll do is we're going to step back a bit because because using our idea we get a much more powerful equation if we consider what we mean by potential. So rather than potential about a unit charge or a positive charge, more generally that is a better equation, and that you've seen before because it is the definition of potential difference in a circuit. Okay, so we can now use this to get a better description of PD, whereas it's the difference in electric potential between 2 points in a field. So if we find the potential at one point and find the potential at another point, we have potential difference, logically. Okay, so PD from last year is more correctly shown as, rearrange that a little bit, work done moving it from V1 to V2. So if we subtract V1 from V2, we can see our change in potential. So if we move from there to there, our final value, subtract the initial value, multiply by Q will give us work done. Okay, now in your data books, that's simplified down, Q delta V. But again, more correctly, we should find the voltage at one place, we should find the voltage at the other, but we can then from that get our change in voltage. Now, circuits, just to pick up on a discussion I had last week, circuits are a quantized version of this. What do I mean? Well, let me just sketch out how I showed you it last year, and hopefully this will kind of make some connections going on in your brain. So a lot of circuits, GCSE, drawn like that, you know, various other bits and pieces. A lamp, for example, no good. For me, I drew them all last year, like electronic engineers draw it, as a whole series of ladders. Okay, remember us talking about potential dividers, for example, and so we had this idea of a ladder of resistance. Okay, so 3 resistors in a circuit, maybe you've got a parallel bit, so you may have, I don't know, an adjustable one, for example, and again, maybe through some sort of bulb or lamp. That was an indicator bulb, but it'll do, the idea. And what we're talking about is finding the potential in our new and improved version, potential before, okay, so let's call that V1, potential afterwards, V2. If you connect your voltmeter across there, you are literally measuring that potential difference. Okay, the difference at the top, the difference at the bottom. And so effectively we are jumping, because of the values of resistance, whatever values they may be. I'm going to have to make that a different one again. So if we got 3 different values of resistor, then what happens is we will have 3 different sizes in potential difference. And effectively it's like changing the gradient on our potential graph, that graph I showed you at the beginning. That one there. Okay. So when we talked about the idea last year, so again looking at this part here, we talked about the idea of sliding down a slope. Okay, big loss of energy, maybe a little loss of energy, and maybe a really big drop in energy. That was the idea we were talking about last year. There's our resistor 2, resistor, and our big resistor. Okay, so the idea was about the size of the drops through these. That gave us our energy out. Okay, V over I. And that's what was causing, as our current flowed down, our voltage drop, our potential difference as it went round. Now, just to be really odd, we really of course know that these are electrons going this way, and this is where we get into the magic area now. You get the same effect if they go up. They're still going to drop that same potential difference. Okay, so even though electrons are really going uphill, well, the reason they're going uphill, pick it up onto there. Okay, so if I draw my little electrons there, they actually flow to the positive end of the battery. This is where, say, the magic comes in. They always seem to flow uphill against the gradient. Okay, so exam questions, really importantly, first check, is it an electron? If it's an electron, then it's going the wrong way. Okay, Franklin came up and made a decision. He made the call that it's going to be positive charges. Our convention is based on positive charges, but unless you're talking about positive ions, the chances are it's going to be an electron moving in the wrong direction. Now I should say, when we get onto particle accelerators, we can of course fire protons and other positive charged particles, so yeah, it can happen. But our work last year about dropping down levels of energy, just like energy changes in electrons around an atom, they are the same as changing energy levels in an energy potential graph. Okay, except unlike gravity, you can have positive charges causing a repelling field as well as negative causing an attracting field. Whew. Right, that's quite a lot of chat there, so you'll probably need to pause, think about that a little bit of information there to kind of talk you through, but it is complicated to get your head around. So at the basic level, potential difference is the work done per unit charge flowing through it, as it was last year. Okay, now just to go back to fields per se, okay, we do, and again I think this is useful, we can think about what happens if you do have potential difference. If there isn't a difference in potential, there will be a charge flow. The charges will move. What do we call that? Current. Okay, so if there's a PD, current flows until you have no difference in potential. So if everything has the same potential, nothing happens. Which means that if you've got a charged up metal object, the charge must be evenly distributed around that, if it's a nice even shape. Okay, it doesn't have to be a points charge, it could be quite a big metal charge like the top of the Van de Graaff machine. Charges will spread out radially from that, okay, from some central point. If you are, again a bit like gravity, got near a surface and the surface is not even, then the field itself is not even. Okay. However, it does mean that the force repelling them apart will mean that they will spread out as evenly as they can. The radius means that they kind of spread around the edge a bit more, but again, this is a slightly dodgy diagram, but the idea is they're trying to even up the force repelling between each one. So it all depends on how far around the surface you're going. Now, it does mean, okay, with that idea there, it does mean that you can end up with some exceedingly sharp changes in potential. Now, let me just give you an example. Just like gravitational fields, to get a certain distance away takes a certain amount of energy. If it was a positive charge, then this will do the work. It will repel it outwards. Okay. But if you're thinking about falling into the hole, then at a certain height, contour above the hole, okay, you'll end up with the same distribution of potential. So we have effectively a potential surface, excuse me, that was a bit wobbly, or an equipotential surface where everywhere around there is at the same height above this surface. So anywhere you put a charge on that circle, it will fall in. Anywhere around that circle doesn't need any energy to keep it going. Now, if we were to take this to be a positive nucleus, that means electrons don't actually need energy to keep them in orbit. Now, nuclei aren't perfectly spherical. We'll come back to it with the nuclear topic, but they're a bit lumpy. You know, protons and neutrons and so on kind of change the distribution, which is why electrons don't form perfect circular orbits. It's more complicated than that if we use that model. But we can use this thing. If we take a voltmeter and we were to place one lead on there, for example, and again, we do this often as a practical, but it's a bit dodgy this year. And we were to test this with a probe. Okay, so we were to take our other probe and we were to test around these various points. What we could do is find the points at which you get the same voltage, and it will depend on spacing. Okay, so actually what you'll find is it changes its position, and effectively we end up with a bigger distance on curves and things like this. And what that kind of shows is that particularly the more curved it is, the more separated out it is. Very bad diagram that I'm doing at the moment, but effectively you end up with a huge concentration of energy, change in potential, a big potential gradient, anywhere there's a really tight curve. And what that means is you can build up a really strong field around tight points, and the smaller the radius of that pointed end, the more intense the field. And we use that with things like lightning conductors, and again I'll demonstrate it with the Van de Graaff machine, but it means that you can get to a point where charge is so repulsive, there's such a strong force, there is such a big change in potential, that actually this will all effectively repel apart charges actively, so the charges will spray off the end. Okay, so we use this in lightning conductors and things like that, and you can actually feel those ions being sprayed away from the surface. Okay, especially if you've got air around here, it becomes ionized, and so your ions is sped up. Okay, but this, I say, these are the ideas of, again, equipotentials. Okay, all of those points along that don't need any energy to move them along. The work is done by the field, or work done against the field to cross the boundary. So again, perfectly right angles to those, just like centripetal force acting on satellites and other circular things. Okay, so really powerful idea. Think it through. As I say, apart from the odd magic that the electrons do the opposite, but again, keep thinking, will it be repelled or will it be attracted? You know, you can work out from the charge of our test object. And definitions wise, it's always a plus, a positive unit charge, but in reality it's usually electrons. So you've got to remember, they're going in the opposite direction, they're going against the field. They're not changing the direction of the field, I should say. Okay, the convention is still the same, but your force, okay, acts in relationship to the field. So negative will go that direction, positive, the force is with the field lines. Okay, so the field lines are the direction a positive charge will move. Great. So, section 4, if one was to say this, what that does is it brings us some useful stuff that we can do some work with. However, while we have got a comparison, let's go back to page 2, I think it was, in the notes, and where we have our comparison with gravitational fields. So where we have a similarity is the idea, say, of potentials. Okay, so cross out the potentials there. I don't know why that's there, because that's all to do with direction of force, isn't it? So if we talk about the potential and again, more correctly or more usefully perhaps, potential differences, where it's our idea of work done. Okay, so change in work, and it will be, for us in gravitational fields, test mass multiplied by change in potential, whereas versus for an electric field, the work done is charge, delta V. So might be a useful way of kind of visualizing it. We're quite used to a voltage in a circuit, voltage being the work done per charge. Well, you know, voltage in a gravitational field is work done per unit mass instead. How much potential energy 1 kilogram has, okay, at a certain point, or how much energy is needed to move that 1 kilogram or 1 coulomb from one point to another point in the field. Okay, so a nice useful little analogy. Have a think about that. I suggest that's probably quite useful to get your head around some of the ideas on potential in gravitational fields. Anyway, back to some other ideas. This is moving us into our next topic, but it does kind of make sense to add it in here. So we're going to go into the next topic, the ability to store charge, okay, which is called capacitance. Really useful in terms of capacitors. That's mainly what our next chapter is about, but I'll give you the concept of capacitance, which is how well these objects will hold that charge. Now, using that, what we can do is we can store more charge on a metal object if we do certain things to it. So for example, if we want to charge things up with a power supply, turn up the voltage. Yeah, that will mean that you can store more charge. But effectively, our ability to store charge is defining us as how well that charge can be held there without it leaking away after we've shoved stuff on. So, not worried about inside, because again, the potential, or the voltage, there we go, potential would be a far better word, the voltage inside is uniform, because if we think about what will happen in a conductor, all the charges will repel apart, and so there'll be no field at all inside here. Interesting thing called the ice pail, Faraday's ice pail. What he realised is charge is always on the outside of a conductor. If you're in a car, in a lightning storm, you're going to be pretty safe, because the charge will always go to the outside. And if you watch high voltage experiments in electronics departments or electrical engineering departments, they basically sit inside a big bird cage, and it's perfectly safe because the charges will always be on the outside. However, using the idea, we can work out the potential at any point in the field on the outside of the surface. We can work it out further differences using that thing there. However, if we define the ability to hold charge, capacitance, as charge per unit volt, okay, so not turning up the voltage because that will force more charge on, that's great, but actually for every volt of the power pack, how much charge can be held on that object, well, we can define it in certain ways, and it doesn't really mean we need to do a lot of thinking about this. It's just we can turn it around and go, well, I take that equation, that's going to equal Q multiplied by 4 pi epsilon naught R over Q, which strangely enough cancels out the Q. So capacitance for a sphere is basically, just rearrange this ever so slightly, 4 pi R. Okay, so that's going to give us our basically our circumference around the edge. Okay, links in with that. Multiplied by the substance, or the ability of the substance around it to resist the escape of the charge. So that's on your data book. Okay, so just be wary. But where does that come from? It literally just comes on how much charge we can hold. But it's logic, size and surrounding stuff. Okay, so just thought bring it in at that point. Now, the complicated bit that I've left till last is down to these graphs. However, there is a very, very useful bit and really, really common. Okay, so if we take our concept of what we got there, okay, so our work done, well, what we've got is we can work out energy levels within a uniform field. Okay, so that is true for all fields. Okay, whereas the initial equation that we had was just for radial fields. In other words, around a single point charge, or something acting as the point of a charge, of a charged field, an electric field. Okay, that's for all fields up there. Excuse me, bring it in. But most of our time we're actually working with uniform fields because it makes much more sense. So, in one of these fields, where we have a whole load of positive charge here, we have relatively negative charge. Okay, and so because of that, we have this level of ladders of voltage between it, just like our equivalent to resistors in a circuit. Yeah, down to that plus V, 0V. So quite useful if you compare it to, say, that electric circuit. And using that idea, well, fairly obviously, the further you go around a circuit, the less voltage you have left. The further down you go, the less away from a positive charge, a positive voltage. Okay, so don't forget plus Q. That means that you have less and less energy as well. So, whereas our definition before on field strength was about the idea of force per coulomb, there's a more convenient one for most things, which is volts per meter. Okay, and it comes from the idea that basically electric field strength is simply V over D, where V is your difference in potential difference, and D is the distance between them. And that kind of hints at a lot of useful stuff as well. So we can make a much, much stronger field simply by reducing the distance between things. Okay, so if we had a resistor and it was really thin or a short length, we can make a really strong field, but that does mean you're more likely to get a spark between them. So the more strong the field is, more intense the field, the greater the field strength, the more likely you are to get a spark across it. Okay, which links us back to that idea just covered, in that what there is there's going to be a maximum ability of, shall we say, insulation of the surrounding medium here, which I hadn't labelled, excuse me. That's your permittivity. If it's a vacuum, then permittivity of a vacuum. So yeah, if the voltage builds up enough, there's a strong enough field for a charge to jump the gap. You'll get sparking if you put those two close together. But it does give us a really nice, convenient unit to use. Okay. Now, just to cover all bases, back to a charged sphere, point charge, radial, okay, i.e. radial field. We get that whole idea of the shape that we had on our plates. Okay, so there's our curve, there's our negative one, there's our positive one building up. If we're using it from the same distance, going off in the same direction, we have our idea of field strength there, E. That's because we've got our repelling plus force, minus force, okay, but on positive charge. Okay, the field does not change shape if we have an electron nearby. It's just it moves in the opposite direction. So that's repelling on a positive charge. Now, if we were to make it a little bit simpler than we've done in the past with the gravitational fields, we can think about the relationships between each. So if we want to talk about electric field strength is potential divided by radius, because potential is for radial field, excuse me, V is 1 over 4 pi epsilon, again, times Q over R. So if we differentiate that with respect to R, then what we'll get is R squared, multipliers as just 1, etc. So we'll end up with the electric field strength. If you want to do the opposites, that electric field strength, say, represents that gradient. There's different ways of doing it. So visually or using calculus, it doesn't really matter. But the link between them is that rate of change of work per unit charge gives you that electric field strength. They link. Now, in terms of bringing it all together mathematically, let's just put it as the gradient for that one equals dV by dr. Okay, as I've got on my graph there, equals E. Excuse me. And if we want to put it all together, this is very much beyond really what you need to do, but just to show where it's coming from, then if we want to find the actual change in potential, we just need to integrate that. So if we take our differentiation work in reverse, substitute it in, we're going to end up with the Q over 4 pi epsilon, that's all a constant, assuming it's a constant field, that is, 1 over R squared dr. Then we end up with that Q over 4 pi epsilon R, okay, which equals V. Why am I doing that? Because that's where our definition came from at the beginning. Okay, so this was all done by calculation, unlike the gravitational one, which was all done by experimentation, which is why we've probably got a more convenient unit. Okay, linking it to circles and so on. So really quite a lot of things, but a lot of things you've seen before, but seen in a slightly different way, because we've used electric circuits, the idea of drops in ladders to give us our drop in energy levels, or drop in energy, as we said last year. So levels of energy as we drop down, even though magically it's electrons are really going up the ladders. Okay, so they're really moving in the opposite direction. Hey ho, never mind. And we can do the complicated mathematics about it, or the more complicated mathematics, do it from the straightforward values to get that. But most importantly, I think for most people, is that you can think of electric fields through that to link together the ideas. So, having a think about what I've just done there, that gives us a reverse. So if you want to take your force, you could do that integration idea, and so we can end up with a nice little equation at the end there. I'm not too worried about it, but you might want to think about that. It's kind of useful. Okay, so that's your equal to work done. Okay, but I think the most important idea is thinking about that idea of energy levels, and I think that looks quite obviously very similarly to energy levels in of electrons around a positive nucleus in an atom. Okay, so direction of the force is important. It doesn't change the energy in those ones, because if you're moving along, because it's perpendicular, therefore the velocity is always changing, therefore it is accelerating because there is a force, so it must all link together, but that's basically equivalent to, or what's giving you the centripetal force. Okay, so back to circular motion. It all kind of comes together. Yeah, the similarities keep running everywhere. Right, hope that helps. Summarise that. It's quite a short topic, but it's one that kind of links to a lot of stuff to help you just kind of visualise. All right, so thanks very much, guys. Sorry it was a long one again, but big topic.